So L is going to be the length of the conductor. And A will be the cross-sectional area of the conductor. All right. Just rewrite area of the conductor. So I'm speaking about a conductor and all of these things, and you have to say, well, what in the world is a conductor? Well, there are different kinds of materials, and a conductor is one that allows electrons to move freely. And so there's a conduction band around atoms, and we've not really, well, we'll probably talk about it, but we've not really gotten too deep into that. But there's a conduction band around atoms, and it's just a band that loosely binds electrons to the nucleus of an atom, and so they're free to move. Okay, they have a lot of freedom there. Whereas insulators are substances or materials that that tightly bound their electrons. Okay, then you have semiconductors, which, depending on what you do to it, can be a conductor or it can be an insulator. All right, so let's describe this mathematically. Boom, 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 boom. R is going to be the resistance. All right, so R is equal to rho times the length of the conductor over the cross-sectional area of the conductor. So basically what we're saying is, as L goes or increases, R is going to increase. It's directly proportional. Whenever you have both the R and the L in the denominator, that is not the denominator, in the numerator, then they're directly proportional. If you have one in the numerator and cross-sectional area in this particular case, or a variable in the denominator, then that's inversely proportional. So as the area goes up, the resistance is going to go down. That's what's meant by inversely proportional. All right, and of course, resistivity, we're considering that to be a constant for a resistor. Maybe it doesn't have to be, but we're considering that to be a constant for this resistor, so it's directly proportional as well. All right, but L and A are things that will be able to change. Okay, so this is the idea. You have standard resistors here that you can purchase from Radio Shack, from some online store, from wherever you go and get your electronics from. And once you purchase it, you're stuck with a certain length and a certain cross-sectional area. If you purchase multiple ones of these things, or multiple resistors, instead of saying these things, but multiple resistors, then you can build new resistors. And we can analyze this geometrically, symbolically, and thus mathematically. So here we go. So we know that we have our geometrical representation. R is equal to rho times L over A. Now let me give you the symbolic representation. This is how we are going to describe our resistors symbolically. Okay, so basically, what's the benefit? Instead of drawing that picture, which takes a long time, we can draw these symbols, which takes a shorter amount of time. That's it. In my mind, it's like it's about being efficient and most likely effective. Typically, what we're going to see is this kind of scenario. You're going to see a resistor connected to some type of load. And I'm saying that wrong. You're going to see a battery connected to some kind of resistive load. Okay. And so we've talked about voltage. We talked about voltage dealing with Millikan's oil drop experiment. And we know that in order for us to move a charge in that conduction band, we're going to have to apply a potential difference, a voltage. Let's just say we have some V2 minus some V1, where V2 is on this side. V1 is on this side and V2 is on this side. We just divide, we subtract them. So we get some potential difference here.